Look at this offshore platform enduring heavy storm waves. Industrial megaprojects like this operate at the physical and technical limits of human capability. They face hostile environmental conditions and billion-dollar financial stakes, where a single structural failure can lead to ecological disaster. Historically, managing these projects relied on a segmented contract approach. Under this model, the project owner hired one company to design the facility, another to purchase the materials, and a completely different firm to build it. Each phase operated as an isolated silo. This photograph shows the dense, chaotic arrangement of vintage land-based oil derricks. In the early days of the energy industry, this compartmentalized method of segmented operations was standard practice for land-based extractions. As the industry expanded into deeper waters and harsher environments, this segmented model created a persistent accountability gap. When engineering plans clashed with construction realities on site, no single entity held responsibility. This fragmentation resulted in schedule delays, cost overruns, and safety failures. To manage the demands of modern megaprojects, the industry developed the EPCIC model. This stands for Engineering, Procurement, Construction, Installation, and Commissioning. EPCIC is a structural mechanism designed to enforce a single chain of accountability. By placing all 5 phases under one continuous contract and one managing entity, the model prevents the cascading failures that plague fragmented billion-dollar environments. The framework begins with engineering. This phase starts with conceptual design, where technicians define the project's technical boundaries, environmental constraints, and operational scope before a single physical action is taken. This photograph captures rows of engineers engaged in meticulous manual drafting. While modern engineering relies on digital systems, the core principle remains the same. Exhaustive, detailed planning is the required foundation for physical execution. From concept, the project moves into the detailed design phase. Here, mechanical, electrical, civil, and chemical engineering disciplines must be perfectly harmonized to ensure the physical structure can support the internal chemical and electrical loads. This diagram illustrates the deliverables: high-fidelity 3D models, accompanied by exact technical specifications. These dictate the performance criteria for every component. Those specifications feed directly into the Bill of Materials, or BOM, an itemized list detailing the exact quantities and sourcing requirements needed. Before finalizing this list, engineers perform a rigorous cost engineering analysis. They test alternative materials and structural designs against the project budget, ensuring cost efficiency without compromising safety parameters. Under the EPCIC framework, engineering dictates the physical reality and risk profile of the entire project. It functions as the foundational layer for risk mitigation. A single theoretical flaw at this stage guarantees physical failure downstream. Once engineering is finalized, the project enters procurement. This phase functions as the logistical execution of the exact technical parameters set by the engineering phase. To fulfill the Bill of Materials, teams deploy supply chain management, or SCM. SCM is the coordinated system of organizations, people, and resources involved in moving a product from a supplier to the final project site. Watch how this global map filters potential suppliers. Through vendor pre-qualification, they are screened for financial stability and technical capability. For critical components, engineers physically audit the remaining suppliers, traveling to manufacturing plants to directly inspect quality control processes before granting approval. Approved vendors then enter the bidding process through a request for proposal, or RFP. An RFP is a formal document that outlines technical requirements and solicits competitive bids, forcing vendors to compete on technical proficiency and delivery timelines. Once contracts are awarded, the focus shifts to execution. This photograph shows the scale of industrial pipes and the orchestrated human labor required to organize these materials on site, illustrating the physical challenge of logistics and material handling. The delivery of every steel beam and specialized valve must be synchronized with the construction schedule. Late deliveries cause bottlenecks, while early deliveries create on-site storage hazards. Procurement teams mitigate supply chain risks by diversifying their supplier base, maintaining buffer stocks for critical items, and securing alternative transportation routes long before the materials are needed. Procurement is the high-stakes translation layer of EPCIC. It turns complex engineering blueprints into massive physical inventory that arrives exactly when the on-site builders require it. The physical build begins with the construction phase. This involves heavy civil engineering, preparing the land, pouring foundations, erecting steel structures, and orchestrating the workforce. This image displays the steel framework and concrete foundations being poured at a dam site. It demonstrates the structural erection required before any specialized operational machinery can be placed. In standard contracts, building the structure is often the final step. However, the complexities of offshore projects required adding a distinct installation phase to the contract model. While construction builds the physical shell, installation is the precise placement and integration of specialized equipment into the broader operational system. Look at this operation. This photograph focuses on workers executing the precise lowering of a massive cylindrical component into the water, highlighting the high-stakes integration required during installation. This photograph shows a complex offshore rig structure being assembled in a flooded shipyard. It captures the environmental challenges inherent in offshore installation, where abstract designs are forced to negotiate with physics and harsh weather. During this phase, there is zero tolerance for error. Even a millimeter of deviation from the original engineering specifications during the installation of a high-pressure valve can cause operational failure. Construction provides the foundation and the walls, but installation embeds the project's critical nervous system. Before the owner accepts the facility, it undergoes commissioning. This is the final validation checkpoint, the testing phase where the fully assembled project is turned on to prove it functions exactly as designed. In this diagram, we see static tests checking structural integrity and verifying correct component installation, measuring alignments before power is introduced. Once verified, the project advances to dynamic tests, where systems are powered up and evaluated under high-stress conditions to ensure performance metrics are hit. This photograph focuses on the heavy, interconnected turbine and generator units installed inside the facility. It illustrates the density of internal systems that must function cohesively during these dynamic performance tests. If tests reveal any discrepancies, engineers execute a fine-tuning process. They adjust calibrations and optimize system flows to ensure long-term safety and peak efficiency. The final step of commissioning is human integration. The contractors transfer technical knowledge, training the client's staff on daily operations, maintenance routines, and emergency protocols. Ultimately, commissioning acts as the project's final audit. It provides hard proof that the unbroken chain of accountability, from engineering through installation, successfully produced a safe, operational reality. This photograph captures an operational offshore drilling rig standing alone in the water. This is the final result of a successful EPCIC contract, a massive asset thriving in a hostile environment. This structure survives because of a strict dependency chain. The success of its commissioning relied on installation precision. That precision depended on procurement logistics, which was strictly governed by the initial engineering design. In this generated video, we see a digital twin. Modern EPCIC execution relies on Building Information Modeling, or BIM. BIM is a digital representation of the physical and functional characteristics of a facility, integrating design, scheduling, and logistics into a single 3D model. These digital tools tighten the EPCIC loop. They allow project managers to monitor supply chains in real time and anticipate on-site construction clashes before materials leave the factory. Furthermore, modern contracts now enforce ESG compliance. ESG stands for environmental, social, and governance criteria, standards that dictate how materials are sustainably sourced, how local labor is utilized, and how the facility impacts the environment. In a global economy defined by extreme physical scale and volatile supply chains, segmented management fails. The integrated EPCIC architecture remains the proven method to enforce accountability and transform abstract blueprints into guaranteed physical survival.